Hi, my name is Tom Duffy. I'm the Applications Engineering Manager for DC-to-DC products at onsemi. Today I'm here to discuss LED lighting and drivers for those applications and the difficulties that can be presented when doing so. When trying to adopt LED drivers for lighting applications, there are a number of issues that arise. Some of the things that you run into are you get different variations of parallel series combinations from manufacturers for the LEDs. The first of which is whether the LEDs are in parallel or series, which will create different load voltages that you have to regulate to. Some of them are very easy to deal with. Some of them just require bucking down from a higher voltage to a lower voltage. Likewise, boosting from a lower voltage to higher. But an interesting problem arises when you have a series combination that results in you having the input voltage straddle the output voltage. That means the input can be above or below the output voltage. This requires a different approach, and we'll talk about that going forward. One of the applications that we're going to talk about involves the Zenigata LED module, which actually has 3 LEDs in series, which creates about 10.5 volts. If you're going to apply it to an MR16 application like this, that means that the input voltage is going to straddle the output voltage. So this is the case where we need the buck boost application. So what do we need to do for the MR16 application? Well, we know it needs to be low cost because it's a light bulb. Secondly, it needs to be pretty small because it has to fit in the end of that light bulb. And we need to accomplish good average load regulation for the LED itself. So let's address the lower cost aspects of the design. We start with an inexpensive controller, the NCP3065. It is a less sophisticated controller by nature. This particular controller doesn't have an integrating loop inside, therefore it creates the problem of having to regulate peak current. So another issue is we need it to be small, which means no big filter capacitors, specifically for AC operation. So when you couple the fact that we have a peak current mode controller and we need small capacitors, it's clear we're going to be regulating the peak of the secondary side. That presents an issue down the line since in a buck boost we want to measure the average output current, but we're really measuring the peak current. If you look at the waveform, the blue area is a plot of the conduction time of the LED for a buck boost. The area under this curve represents the average current that goes to the LED. Now, if we just keep the peak constant and we move V in, we're going to find that that area will change. And that results in the curve that you see in the upper left corner. As Vn goes up, the average output current will increase as well. The error in average output current can be corrected by adding a voltage feed-forward divider to the feedback node. What this has the effect of doing is bringing the end current back down to where the start current was. It will result in a little bit of tolerance, but it will correct much of the error. Another complicating factor is when we have AC operation versus DC operation for the MR16. We're going to have a sinusoidal 60 Hertz input, and we already know we can't have big filter caps to bridge those low voltages. So we are going to have a situation where the sinusoid will still exist on the input, we full bridge rectify it, and we have some dropouts. When those dropouts get below about 3 volts, we'll have absolutely no current going to the load. This results in a lower average current overall to the LED. Now, this can be offset by adding an RC diode circuit, which can help detect whether we have AC or DC operation and boost the current during the high times, thus compensating out some of that average current. So as a comparison, if you look at the illustration here, these two curves represent AC operation and DC operation line regulation. And across the entire line voltage, you can see these two curves are within about 50 milliamps of each other. So it's a pretty good method for compensating AC versus DC. Transient surge protection is another thing you may want to consider depending on the application. Landscape lighting is a good example of this since the source tends to be very inductive. Another thing you might want to consider is fusing the input, considering shorting of the output or either terminals of the LED to ground. Probably the most important protection that we can think about is open circuit protection. This is a current regulator. If you open the circuit, it's going to go to full duty cycle and produce large voltages on the output. The way we implement it in this design is to add a Zener clamp that feeds back to the current limiter section of the NCP3065 and limits the peak voltage on the output. So using the concepts that we've discussed, onsemi has produced a small form factor reference design for use with the Sharp Zenigata LED module and is being used in MR16 landscape lighting applications today. Thanks for your attention. Once again, my name is Tom Duffy, and if you need any more technical detail on this or any other reference design from onsemi, please visit our website at www.onsemi.com.